Welcome to AM radio. In this video, you will draw upon your knowledge of semiconductor devices, amplifiers, and oscillator circuits, and learn to apply this knowledge toward understanding the various circuits contained in a typical superheterodyne AM receiver. To better understand the operation of the AM receiver, you should first understand the basic concepts of modulation. Since the beginning, when it was discovered that electrical impulses, called radio waves, could be sent from one point to another, man has used these waves for the purpose of communication. Some of the first forms of electronic communication were very crude by today's standards, consisted primarily of turning an oscillator circuit on and off in a series of pulses which could be recognized as coded letters. Next, man found a way to apply his voice directly to the output of the oscillator circuit, thereby allowing other persons at a distant point to hear what was being said. This allowed him to transmit not only his voice, but music as well. This process of applying sound to the output of the transmitted radio wave became known as modulation. Before going any further with modulation, let's first examine the characteristics of the AC wave. All AC waves have three basic qualities. These are amplitude, frequency, and phase. Therefore, if you wish to modulate any AC wave, you must vary either the amplitude, frequency, or the phase of the carrier wave being broadcast. By varying the amplitude of the transmitter output, you can create an amplitude-modulated waveform. This form of modulation is most often referred to as AM. In the same respect, by varying the frequency of the transmitter output, you can create a frequency-modulated waveform. This form of modulation is most often referred to as FM. Or by varying the phase of the transmitted output, you can create a phase-modulated waveform. This form of modulation is most often referred to as PM. In your study of electronics in You Can Do's Basic Series, you have already become familiar with the various amplifier and oscillator circuits. With the information being presented to you in this video, you will begin to piece together your knowledge of these circuits to understand the process used in demodulating and reproducing the information which is transmitted on a radio wave. Since amplitude modulation, frequency modulation, and phase modulation are so vastly different in their modulation and demodulation processes, we will cover these in separate videos. This video will concentrate on the amplitude modulated signal and phase modulation when AM stereo is covered later in the video. In most practical modulation applications, the audio information to be transmitted must be carried through the air on a frequency greater than that of the audio frequency range. This signal is referred to as the carrier wave, and its frequency will generally be many thousand times higher than the audio frequency being transmitted. When the carrier wave is being modulated with the audio signal, the amount of amplitude modulation being produced will determine the frequency of the sound at the speaker of the receiver. As you will see, the process used to modulate the carrier wave can be a very simple one. In this simple circuit, we are using an audio signal to control the current flowing through the amplifier stage, which is also being fed by a radio frequency oscillator. Basically, we have varied the amplitude of the oscillator signal with that of the audio signal. As you may have noticed, the amplitude of the RF carrier wave is no longer constant, but instead is varying at the rate of the audio information. In a practical circuit, the percentage of modulation may vary from 0 during a pause in the program to 100% during a loud portion of the broadcast. To 100% modulate a Class C amplifier, the audio amplifier must be capable of supplying an output equal to 1/2 of the Class C power input. In other words, if the power being fed into the Class C amplifier is 100 watts, then the audio power amplifier must be capable of supplying 50 watts of audio power to be able to 100% modulate the RF carrier wave. This causes the RF carrier wave to vary between 0 to 150 watts at the output of the Class C amplifier. One of the simplest methods used to modulate the RF carrier wave with audio information is called absorption modulation. Here you see a circuit which utilizes the absorption modulation technique. Basically, it is a Hartley oscillator with a single button microphone that is inductively coupled to the antenna circuit. Most of the RF carrier energy being fed into the antenna circuit by the oscillator will be radiated by the antenna when there is no modulation on the microphone. However, some of the energy from the oscillator circuit is fed into the microphone loop and is dissipated by the resistance of the microphone in the form of heat. The resistance of the microphone will vary directly with the audio rate of any sound which causes its diaphragm to vibrate. As a result, the amount of RF energy being absorbed and dissipated in the form of heat by the microphone will vary with the audio frequency. Since the microphone is absorbing more or less power from the oscillator output, the antenna finds itself with more or less power to be radiated. This variation of the RF energy from the output of the antenna is referred to as amplitude modulation. Since most modulated radio frequency stages are biased Class C, the output of the oscillator circuit will be narrow pulses of direct current. These narrow pulses of direct current will then be fed into a tank circuit to produce the sinusoidal radio frequency AC output, which is required for the carrier signal. It is important to understand that in single-ended circuits, the flywheel action of the tank circuit is responsible for the reproduction of the second half of the radio frequency AC cycle. The absorption loop of the microphone circuit acts as a partially shorted turn which is magnetically coupled to the oscillator's tank circuit. As the resistance of the microphone changes, so will the effective inductance of the absorption loop. This causes the inductance of the tank circuit to change, which results in a change in the frequency of the oscillator output, as well as a change in its amplitude. The simultaneous change in both the frequency and the amplitude of the carrier wave produces unwanted distortion. Therefore, this form of modulation is impractical by today's standards and is rarely used. Here you see a block diagram of a simple series modulated AM transmitter. To reduce the frequency modulation in the AM transmitter, it is necessary to place one or more buffer stages between the RF oscillator and the modulated Class C amplifier stage. As a precaution, all stages should be adequately shielded and neutralized for proper operation of this circuit. As you can see, a continuous RF carrier wave is provided by the RF oscillator through a buffer amplifier, then through an RF amplifier, and into a Class C modulated amplifier. The modulating audio signal is taken from the microphone and fed into a preamp stage, then into an audio frequency amplifier stage, and then into the modulation amplifier. The modulation amplifier is then used to control the power output of the Class C modulation amplifier, which is then fed into a linear amplifier to be radiated by the antenna. Many of today's transmitters make use of frequency synthesizers to generate a highly accurate and stable frequency to be used for the transmitted carrier signal. Frequency synthesis is achieved by employing digital IC circuits to obtain the exact frequency from a single fixed frequency oscillator circuit. As you can see in this particular circuit, the phase lock loop IC is used to synchronize the output of the transmitter oscillator with that of the crystal-controlled oscillator's output, both in phase and frequency. At this time, we will pause for a short review of the recently discussed material. It is important that you have a basic idea of how the signal is transmitted to better understand the operation of the superheterodyne receiver. So far, you have seen that an AC wave has three basic qualities. These were amplitude, phase, and frequency. You have seen that by varying the amplitude of the AC wave, you can create an amplitude modulated signal. Or if you vary the phase of the AC wave, you can create a phase modulated signal. And in the same respect, by varying the frequency of the AC wave, you can create a frequency modulated signal. In order to transmit audio information through the air, you must have a carrier frequency many times greater than that of the audio frequency rate. You have seen that a method referred to as absorption modulation can be used to transmit an amplitude modulated wave. However, due to certain drawbacks, this circuit is seldom used. To overcome the limitations of the absorption modulation technique, it becomes necessary to place one or more buffer stages between the RF oscillator and the modulated Class C amplifier. In its simplest form, the basic operation of the AM transmitter is to increase or decrease the radiated power of the radio frequency oscillator circuit used to create the carrier wave. Now that you have a better understanding of how the AM signal is created, it is time to see what happens to the modulated signal after it reaches the AM receiver. The operation of the AM receiver is very simple in nature. Basically, the AM receiver receives the transmitted modulated radio frequency signal, then removes the information contained in the carrier wave. Next, it reproduces this information back into a duplicate of its original form, which of course is that of the sound wave that we are accustomed to hearing. This entire process is accomplished through 5 basic functions. First, it must intercept the radio frequency signal. Second, it must have the ability to select the desired signal. Third, it must amplify the weak signal. Fourth, it must separate the carrier wave from the audio information. And fifth, it must reproduce the information in a usable form. By now, you should already start becoming familiar with this simple block diagram. It is a typical block diagram of a super heterodyne AM receiver. It has become the standard for most AM radio applications. This system received its name because of the fact that it employs the principle of heterodyning. By definition, heterodyning is when 2 signals are mixed in a nonlinear device, which produces a signal at its output which contains 4 different signals. These are the RF signal, picked up by the antenna, the oscillator signal, which is mixed with the RF signal, the sum of the 2 signals, and the difference of the 2 signals. At this point, we will examine what happens to the RF signal when it reaches the super heterodyne receiver. First, the weak incoming RF signal is amplified by the first stage of the circuit, which, as you can see, is the radio frequency amplifier. Next, the amplified RF signal is fed into the mixer circuit, where it is combined with the frequency being generated by the local oscillator circuit. At this point, the signal is being heterodyned and converted into a different frequency called the intermediate frequency, or IF for short. The intermediate frequency signal is then fed into another amplifier stage, which further increases the amplitude or the strength of the signal. From here, the IF signal is fed into the detector stage, where the carrier wave is separated from the audio information. Only the audio information is allowed to pass through this stage. Finally, the audio signal is again amplified by the audio frequency amplifier stage to a level sufficient to drive the speakers at the output of the system. At this point, I will mention there are super heterodyne systems available which incorporate both the mixer and the local oscillator stages into one single unit. This stage is then referred to as the converter stage. Before proceeding into more detail of the operation of each of the various stages contained in the AM super heterodyne receiver, we will quickly review the information just discussed. You have just seen that the super heterodyne receiver consists of 6 basic circuit blocks. These, of course, were the RF amplifier, mixer, oscillator stages, the IF amplifier, the detector circuit, and the audio frequency amplifier stage. You also learned that in some super heterodyne receiver designs that the mixer and oscillator stages are combined to create a new stage called the converter stage. You also learned that the mixer stage actually contains 4 different signals. These were the incoming RF signal, the local oscillator signal, the sum of the 2 signals, and the difference of the 2 signals. And you learned that a radio receiver must perform 5 basic functions. It must be capable of intercepting the radio frequency carrier wave, selecting the desired frequency, amplifying the weak signal, separating the carrier wave from the transmitted information, and it must be capable of reproducing the audio information back into a usable form. Now that you have a better understanding of the function of each of the blocks contained in the superheterodyne receiver, let's continue with the video and learn more about each of these stages. We will begin with the RF amplifier stage. As mentioned, the first stage we will learn about is the RF amplifier stage. In the less expensive AM superheterodyne systems, you may not find an RF amplifier stage, but rather you may find a system similar to the one you are now viewing. In this system, the RF signal, which is detected and picked up by the antenna, is fed directly into the mixer oscillator circuit. Even though this system does not contain a radio frequency amplifier stage, it must still contain an RF section. This generally consists of a tuned circuit at the input of the mixer stage. Remember, the RF section must be present to intercept the radio frequency signal. You will find, though, that most AM receivers will usually contain the RF amplifier stage. In some of the more sophisticated AM/FM receivers, it is common to find two radio frequency amplifier stages. These stages are generally used to amplify both the AM and FM bands. You will learn more about this in your study of FM radio. The key advantages to using the RF amplifier stage include better sensitivity, improved signal-to-noise characteristics, and improved image frequency rejection. Since the RF amplifier stage will boost the incoming signal by 100 times or more, it is able to pick up the much weaker signals, like those being produced from distant stations. Due to its inherent characteristics, the mixer stage will typically generate large amounts of electrical noise. Therefore, by amplifying the weak RF signal, the signal-to-noise ratio is greatly increased. The signal-to-noise ratio is a relation of signal power to noise power within the given circuit. Since most of the stages following the mixer stage will amplify the noise being generated by the mixer stage, the RF amplifier almost becomes a necessity for distant stations. If the signal power from the RF amplifier stage is 10 times the power generated by the thermal action in the input circuit, resistance of the mixer stage, the signal-to-noise ratio will be 10. This gives the RF amplifier a much better chance of overriding the mixer noise. The RF amplifier section will usually contain two tuned stages which are gang tunable to the incoming signal. In other words, both stages are tuned at the same time. This greatly increases the strength of the desired signal and at the same time greatly reduces the strength of the unwanted frequencies. Here you see a PNP RF amplifier stage with a tuned input and a tuned output. This circuit is commonly found in many of the older style automobile receivers. Notice that the resonant circuits are tuned by varying the inductance instead of the capacitance. This type of tuning is called permeability tuning. By now, you may have noticed that the base of transistor Q1 is being supplied with a voltage potential from the automatic gain control circuit labeled AGC. The AGC circuit is designed to keep the base of Q1 negative with respect to the emitter. This is necessary since Q1 is a PNP device. Basically, the AGC voltage being applied at the base of Q1 will be less positive than the emitter voltage. At this time, we will quickly examine the operation of this simple circuit and see how the AGC signal is able to control the output of the RF amplifier stage. When a strong signal is received, the AGC voltage will change to reduce the gain of the stage. To accomplish this, the AGC voltage will make the base more positive, which will cause the difference of potential between the emitter and base to decrease. This will result in a reduced gain in the stage. As you can see, the current flows from the negative side of the power source through the C5L3 combination, which forms the tank circuit, then into the collector of transistor Q1. The collector current then combines with the base current and flows through the transistor, through our resistor R2 and back to the positive side of the power source. The signal being fed from the input-tuned tank circuit and the feedback signal from the automatic gain control are used to control the operation of this circuit. The RF amplifier stage is generally operated as a Class A amplifier. Here you see another small signal RF amplifier stage. This amplifier uses an NPN bipolar junction transistor with degenerative voltage divider bias and emitter stabilization. Resistors R1, R2, and R3 are used to bias the transistor for Class A operation. The circuit also contains two resonant tank circuits. The input tank circuit consists of inductor L2 and capacitor C2. The output resonant tank circuit consists of inductor L4 and capacitor C6. As you should have noticed, capacitors C2 and C6 are both variable capacitors, and they are gang-tuned. The purpose of gang tuning is to allow more than one stage to adjust at a time. By adjusting both the input and the output tuned circuits simultaneously, you can increase the selectivity of the RF stage. Capacitor C4 is used to hold the emitter bias voltage constant even when the input signal voltage applied at the base causes a variation in the collector current, which results in more current flow through emitter resistor R3. Basically, capacitor C4 forms a low impedance path from the emitter to ground, which results in a decrease in the degenerative effect that would otherwise reduce the gain of the stage. Notice that all the common leads of the RF amplifier stage are brought to one point. This is a very important thing when designing high-frequency circuits. Using a single ground point becomes a necessity if minimum interaction between stages is to be obtained. Also, all leads should be as physically short as possible. Otherwise, the long leads may produce a self-sustained oscillation, or they may interact and cause oscillations in other stages. To prevent unwanted inductive coupling between the various stages of the superheterodyne receiver, the tuned tank circuits are usually encased in metal shielded cans. Inside the can, the stray RF currents are induced onto the inner walls of the can and sent to ground. The high-frequency currents will travel on the walls of the can due to a phenomenon referred to as skin effect. These shielded cans are used in both the RF and IF stages of the receiver. A properly shielded can will prevent degeneration, regeneration, oscillation, distortion, parasitics, and overall instability. Now we will examine the heart of the superheterodyne circuit, the mixer stage. Even though the tuned RF amplifier stage has many desirable features, it would have a very limited range of usefulness if the receivers using it could only work at the frequencies received, selected, and amplified by this stage. Therefore, a method of converting these radio frequencies into a lower frequency range, called the intermediate frequency, becomes necessary in order to have a practical radio receiver. This is accomplished with a frequency conversion circuit, the mixer stage. As you may have noticed, the output of the RF amplifier stage is fed into the mixer circuit. The mixer stage performs the operation of frequency conversion by heterodyning or beating together the desired incoming frequency with the frequency being supplied by the local oscillator. This produces two new frequencies at the output of the mixer circuit. These are the sum and the difference of the two heterodyne signals. The difference signal produced by the mixer stage is then fed into the intermediate frequency amplifier stage. In order to produce an intermediate frequency signal that will remain constant in frequency and can still vary in amplitude, the local oscillator circuit must be tunable. The local oscillator stage in the superheterodyne receiver is designed to operate at a predetermined frequency above the incoming RF signal. The local oscillator will usually operate at a frequency of 455 kilohertz above the incoming RF signal. For example, let's say that the RF amplifier is tuned to 600 kilohertz. Then the local oscillator must be tuned to a frequency of 1055 kilohertz. This way, when the signals are heterodyne, they will produce a different signal of 455 kilohertz. The oscillator configuration most commonly used for the local oscillator stage will either be the Hartley or Armstrong circuits. The ability of the local oscillator to maintain this difference frequency for all selected RF frequencies is called tracking. For proper operation of the receiver, it is necessary to track the tuning of the oscillator stage, the mixer stage, and the RF amplifier stage. This way, when the RF amplifier and mixer stages are tuned to a desired frequency, the local oscillator will always be exactly 455 kilohertz higher than the incoming RF signal. This is accomplished by using variable gang capacitors for the RF, mixer, and local oscillator stages. Even in the more elaborate receivers, which contain more than one RF amplifier stage, these stages will be ganged together for proper tracking. It is important to understand that the local oscillator is instrumental in determining the frequency to which the receiver is tuned. As you already know, the intermediate frequency, or IF amplifier stage, will always be tuned to 455 kilohertz. If the RF amplifier is tuned to a different frequency, without also tuning the local oscillator circuit with it, the difference frequency would no longer be 455 kilohertz, and the receiver would no longer be sensitive to the selected frequency. Therefore, the mixer circuit will usually have two tunable sections. These are made up of the tuned circuit in the local oscillator and the input to the mixer stage. Before continuing with the IF and detector circuits used in the AM superheterodyne receiver system, we will pause for a short review of the material just discussed. The pure AM radio may not contain an RF amplifier stage, but it must contain an RF section. The RF section may be nothing more than the antenna feeding directly into the input of the mixer stage. The major advantages of using the RF amplifier stage are a better sensitivity, improved signal-to-noise characteristics, and improved image frequency rejection. The RF amplifier stage will generally have a tuned input and a tuned output. These tuned circuits will normally be gang-tuned. To prevent unwanted inductive coupling between the various stages, the tuned circuits are usually encased in a shielded can. The stray RF currents are then induced onto the inner walls of the can and sent to ground. The mixer stage is used to heterodyne or beat together the incoming RF signal with that of the local oscillator stage. The output of the mixer stage will always be tuned to 455 kilohertz. This is an industry standard. The local oscillator section will be tuned to 455 kilohertz above the frequency of the incoming RF signal. The local oscillator is usually constructed with the Armstrong or Hartley configurations. The RF amplifier, local oscillator, and mixer stages are always gang-tuned for proper selectivity of the desired station. This concludes review number 3. Next, we will examine the intermediate frequency amplifier stage and detector section of the AM receiver. After the mixer stage heterodyned the local oscillator signal with that of the incoming RF signal, a new lower frequency called the intermediate frequency was formed. This intermediate frequency is fed into the IF amplifier stage. Many of the older, less expensive table model AM receivers contained only one IF section. However, in today's modern AM/FM receivers, it is common to find as many as 4 intermediate frequency amplifier sections. In these modern receivers, the majority of the gain developed across the incoming signal is produced in the IF sections. The intermediate frequency amplifier stages are factory tuned to 455 kilohertz. This allows the stages to produce optimum gain with a sufficiently narrow bandwidth. The narrow bandwidth improves the sensitivity and selectivity of the incoming signal, but in the same respect, it also produces a poorer signal for the audio frequency amplifier stages due to the fact the sideband frequencies are squeezed out. Many of today's modern receivers use components other than LC tank circuits to provide the intermediate frequency selectivity. Crystal filters are becoming increasingly more popular. This is due to the fact that the crystal filter has a typical Q factor of nearly 1,000. The primary difference between the intermediate frequency amplifier stage and the preceding stages is that the IF amplifier does not require tracking, since it is preset to a defined frequency limit and will remain tuned to this frequency regardless of the input RF signal. Since the IF amplifier stage operates in the low radio frequency spectrum, there are many transistor amplifier circuits which may be used to perform this function. Typically, the input and output coupling of the IF circuits will contain a tuned section. This results in a high gain for the incoming signal with an effective rejection for all frequencies to which the stage is not tuned. There are several methods which may be employed to produce either a narrow or a variable IF bandwidth. The coupling between the primary and secondary of the IF transformers can be adjusted from a less than critical condition, which produces a narrow bandwidth, to an overcoupled condition, which results in a much wider bandwidth. The IF transformers are generally enclosed in an aluminum shielded can to reduce the stray electromagnetic lines of force which may affect the operation of the circuit. Notice the short dashed lines surrounding the tuned circuits. This indicates that the circuit is encased in a shielded can. Proper shielding will decrease or prevent degeneration, regeneration, oscillation, distortion, and other undesired effects. Most IF transformers will use a fixed value mica capacitor placed in parallel with the coils to form the tuned circuits. Once the intermediate signal has been sufficiently amplified by the IF section, it is fed into the detector unit. The primary function of the detector unit is to demodulate or separate the audio information from the carrier signal. Various detector circuits have been used since the early days of radio, with each having its own advantage at the time. However, the most commonly found circuit which has been used over the past several decades is the simple diode detector circuit, much like the one you are seeing now. Here you see the process used to demodulate the incoming signal. It consists of 3 steps. These are: first, the RF carrier envelope is rectified so that only half of the signal gets through. Second, the audio information is separated from the RF carrier. At this point, the carrier is sent to ground. And third, the audio information is separated from its DC component. To better understand how this process is accomplished, let's see what happens to the modulated signal when it reaches the detector circuit. First, the output from the intermediate frequency amplifier section is inductively coupled through the tuned tank circuit, located at the input of the detector stage. The voltage being developed across the secondary of the tuned circuit will be the modulated carrier wave. Next, the modulated carrier wave is fed into the detector diode D1. At this point, the carrier becomes rectified, since the diode will only allow current to flow in one direction. Only half of the modulated signal will pass. Even though only half of the modulated carrier passes through the diode, it will still consist of 3 parts. These are the radio frequency carrier wave, the DC component on which the information is riding, and the audio frequency component. The DC component will be the average amplitude of the voltage developed across capacitor C3. From here, the RF carrier wave is eliminated by capacitor C4. The value of C4 will be chosen to offer a low impedance to the RF component and a high impedance to the much lower audio frequency component. This results in capacitor C4 bypassing the RF carrier wave to ground while blocking the audio frequency signal. The audio signal is then passed through capacitor C5 where the DC component is removed. As you have seen, the audio signal that was transmitted appeared to be riding on the top and bottom of the RF carrier envelope, whereas in reality, the audio signal was never actually there. Instead, the amplitude of the peaks of the carrier wave were varied so that the audio signal appeared to be riding on the RF energy. Also, since the positive and negative peaks both contained the apparent audio information, only half of the modulated envelope was necessary for demodulation of the input signal. As you have seen, the AM detector circuit is a very simple one and easily understood. Before we continue into the final stages of the AM superheterodyne receiver, let's review some of the information just discussed on the IF section and detector section. In some of the more sophisticated AM/FM receivers, it is common to find as many as 4 IF amplifier stages. The intermediate frequency amplifier stages are factory tuned to 455 kilohertz, which allows the stages to produce optimum gain with a sufficiently narrow bandwidth. The bandwidth between the IF stages is determined by the coupling of the IF transformers. They are adjusted between a less than critical to an overcoupled condition. The IF transformers used to couple the signal between the IF stages are generally encased in an aluminum can to reduce the possibility of stray electromagnetic lines of force affecting other parts of the circuit. The primary function of the AM detector circuit is to separate or demodulate the audio information from the carrier signal. The AM signal is demodulated in 3 simple steps. First, the amplitude modulated envelope is rectified. Second, the carrier frequency is coupled to ground, leaving the audio information intact. Third, the DC component is removed from the audio signal. This concludes review number 4. Next, we will examine the audio frequency amplifier stages. The final stage of the superheterodyne receiver is the audio amplifier stage. The purpose of the audio amplifier stage is to increase the level of power of the audio frequencies produced by the detector stage to a value sufficient to drive the speaker system. Here you see a general purpose 4-stage transistor amplifier capable of producing 10 watts of power if proper heat sinks are used with the power transistors in the final stages. The first 2 stages are direct coupled. Notice that they use both an NPN and a PNP transistor. The resistors in these stages are chosen so that both transistors are biased to operate at the Class A operating point of their characteristic curves. When a positive going signal is applied at the base of Q1, it will cause this NPN transistor to turn on and conduct an increased collector current flow. In effect, Q1 will produce an amplified reproduction of the input signal. The output of transistor Q1 will be 180 degrees out of phase with the input signal. The 180-degree phase shifted signal is then fed into the base of transistor Q2. Since the base of Q2 is directly coupled to the collector of Q1, the negative going signal from Q1 will forward bias transistor Q2. Remember, Q2 is a PNP transistor. The forward bias condition on Q2 will cause the collector current of Q2 to increase. The increased current flow through Q2 causes the current through resistor R6 also to increase. As the current through R6 increases, so will the voltage drop being developed across it. As you should have noticed, R6 is a potentiometer which is being used as the volume control device. The positive going signal being developed across R6 is then fed through coupling capacitor C3 and into the base of transistor Q3. The third stage, which includes Q3, is an NPN power amplifier, which should be capable of supplying a minimum of 1/2 watt of power to drive the following push-pull stage adequately. The fourth stage uses 2 NPN transistors in a push-pull configuration to provide the power required to operate the speaker systems. As you may recall from your study of amplifiers, the push-pull configuration is generally operated in the Class B or Class AB modes. Resistor R10 is a thermistor, which is a negative temperature coefficient resistor. As the temperature of the circuit increases, the resistance of R10 will decrease, thereby decreasing the forward bias, which reduces the collector current of Q4 and Q5. This prevents thermal runaway of the final stage. There are many audio amplifier configurations which may be used as the final stage of the superheterodyne receiver. They may vary from single transistor, low-power Class A amplifiers capable of driving an earphone up to multi-stage power amplifiers capable of delivering several hundred watts of power into a speaker system. For more information about audio amplifier circuits and their operation, review your You Can Do Part 5 amplifier video. The next part of this video examines AM stereo. You will learn how the AM stereo signal is modulated and demodulated. It is our belief that AM stereo will play a major role in today's audio entertainment broadcasting. We would like to thank Motorola Incorporated for providing us with the technical data being presented to you in this portion of the video. An industry standard for AM stereo broadcasting is the Sequam system, which is a registered trademark of Motorola Incorporated. The Sequam system was originated by Motorola over a period of 7 years. As of August 1992, there were 615 AM stereo broadcast stations located across the United States, serving an estimated 235 million people. Sequam is a system which uses amplitude modulation for the main carrier and phase modulation for the stereo information. The Sequam system uses circuits commonly found in both AM and FM broadcast systems. Since the Sequam system relies heavily upon phase modulation for creating the stereo effect, we will study the phase modulation process first. A true phase-modulated circuit will shift the phase of the carrier in accordance with the audio modulating signal. For example, here you see a single cycle of a 1 kHz audio signal with a phase-modulated 20 kHz RF carrier wave. As you can see, there are 20 cycles of carrier wave for every 1 cycle of audio signal. But what happens when the audio signal doubles? When the audio signal is increased to 2 kHz, there are still only 20 cycles of carrier frequency. The only thing that changes is the phase angle of the RF carrier wave. As you will begin to see, the carrier does not change frequency, just the phase. To better understand how this works, we will examine a simple phase modulator circuit. Here you see a block diagram of a typical phase modulator circuit. Notice that the crystal oscillator and the audio input both feed into the amplitude modulator stage. The output of the amplitude modulator stage will be a standard in-phase amplitude modulated RF wave, the frequency of which will be that of the crystal oscillator. The crystal oscillator also feeds the 90-degree phase shift network section. The output from the 90-degree phase shift circuit is a constant frequency, constant amplitude, 90-degree phase shifted RF carrier whose frequency is also that of the oscillator circuit. The output from the phase shifting network and the output from the amplitude modulator are then fed into a summing junction, where the in-phase amplitude modulated carrier wave combines with the 90-degree phase shifted signal from the phase shift network. When the two signals combine, they will vary in phase as well as amplitude. To illustrate how this happens, let's examine this vector diagram. E1 is the 90-degree phase-shifted reference signal. Its amplitude and frequency will remain constant. E2 is the amplitude-modulated signal being fed from the amplitude modulator stage. When the two signals combine, they create a new signal that has a phase angle between 0 to 90 degrees from the reference signal. We will call this new signal, which is in reality the phi signal, E3. Notice that when signal E2 from the amplitude modulator has a low amplitude, the phase angle between the reference signal E1 and the sum signal E3 is very small. Now notice the phase angle between the reference signal and the sum signal when the amplitude of the modulated signal increases. The phase angle between the two becomes much greater. As you can see, the phase angle between the resultant signal E3 and the reference signal E1 can be made to vary in accordance with the modulated signal E2. You should also notice that as a modulated signal increases or decreases in amplitude, the resultant signal E3 also increases and decreases in value. This results in amplitude modulation riding on the phase modulated signal. The resultant signal, E3, is next fed into the limiter stage. The primary function of the limiter stage is to remove all amplitude modulation from the phase modulated signal. We will not go into detail on how the limiter stage performs this task. You will examine the limiter stage in more detail in the You Can Do FM video. Next, the signal is fed into a multiplier stage. Generally, the phase shift between the reference signal and the modulator signal is held between plus or minus 15 degrees from the value of the phase angle when there is no modulation. This small phase shift is usually too small for practical applications. So the signal is generally fed into a frequency multiplier circuit to increase the phase shift and corresponding frequency change to the desired value. The frequency multiplier is usually a Class C amplifier. Now that you have a basic understanding of the operation of the phase modulated circuit, let's examine a simplified AM stereo broadcast station transmitter. Here you see a simplified block diagram of the Motorola Sequam stereo broadcast system. Notice that the box marked exciter contains the circuitry necessary to produce the stereo information to be transmitted. This section of the broadcast system contains the matrix, which is used for the L plus R and L minus R signals. The QAM modulator contains both the I and Q modulator stages, and the limiter stage is necessary for removing all amplitude modulation from the phase modulated phi signal. The basic operating principle of this system is very simple. The phase modulated phi signal, which leaves the limiter stage, is fed to the transmitter in radio frequency form and is used as the broadcast carrier frequency for the transmitter. The L plus R audio signal is fed into the transmitter audio input, where it amplitude modulates the phase modulated RF carrier in the normal fashion, thus recreating the standard monaural AM signal. This allows all existing AM receivers the ability to receive the AM stereo broadcast in monaural instead of stereo. Stereo reception is only possible with the use of the proper Sequam decoding circuitry. Here you see a more detailed view of the heart of the Sequam stereo broadcast system, the Sequam encoder. Notice that pure quadrature is generated by taking the L plus R and the L minus R audio signals and modulating the two balanced I and Q modulators, which are fed with the radio frequency signals out of phase by 90 degrees. The I modulator is fed with an in-phase RF carrier. The Q modulator is fed with a 90-degree phase-shifted RF carrier. As you can see, the 90-degree phase shift is derived by using a Johnson counter, which divides the oscillator's frequency by 4 and automatically provides digital signals precisely 90 degrees out of phase for the balanced modulators. The output of the oscillator stage must therefore be 4 times the broadcast station's carrier frequency. You may have noticed that the RF carrier is also inserted directly from the Johnson counter into the summing junction, along with the outputs of the I and Q modulators. The output of the summing network will be a pure quadrature AM stereo signal. Next, the signal is passed through the limiter stage, which removes the incompatible amplitude modulated components from the signal and leaves only the phase modulation sidebands. The output from the limiter stage is then amplified and sent to the broadcast transmitter in place of the crystal oscillator's signal. The left and right audio signals are precisely added and sent to the audio input terminals of the broadcast transmitter, where they are used to amplitude modulate the phase-modulated RF carrier. By now, you should start to understand how the CQAM system is capable of broadcasting a stereo signal and still maintain the relatively narrow bandwidth used in AM broadcasting. Before proceeding with the decoding system used for AM stereo, we will pause for a short review of the material just discussed. CQAM, which is a registered trademark of Motorola Incorporated, is a system which uses amplitude modulation for the monaural part of the signal and phase modulation for the stereo part of the signal. CQAM has become an industry standard for AM stereo. In phase modulation, the phase angle of the signal changes, whereas the frequency of the signal remains constant. The function of the limiter stage is to remove all amplitude variations from the phase-modulated signal, thereby leaving only the phase-modulated sidebands at its output. The I signal in the phase modulator system contains the monaural information. The I signal will be in phase with the carrier signal and is used to modulate the RF carrier in the transmitter. The I signal requires linear amplification for distortion-free power gain. The Phi signal is an almost quadrature phase-modulated signal that is used to carry the stereo information. The Phi signal becomes the transmitter's RF carrier frequency and will be phase-shifted by an amount somewhat less than 90 degrees. The Phi signal can be amplified by a Class C amplifier and therefore does not require linear amplification. This concludes review number 5. Next, we will examine the AM stereo receiver. The standard AM radio envelope detector will not recognize the existence of the phase-shifted stereo information being transmitted by the CQAM AM stereo system. However, the envelope detector will detect the monaural portion of the stereo broadcast and reproduce this information in the usual manner. This allows all existing monaural AM receivers the ability to receive and detect the AM stereo broadcasted signal. However, the detected signal will be reproduced in monaural form, not stereo. To recover the stereo information, a system of phase detectors must be used. Here you see a simplified block diagram of a quadrature synchronous detector circuit. As you can see, it consists of the I and Q demodulator sections, a VCO or voltage-controlled oscillator with phase lock loop capabilities, and a 90-degree phase shift network. For this system to function, a reference phase must be derived from the broadcast signal. This is accomplished through the use of the voltage-controlled oscillator section. Devices which are primarily responsible for the operation of the synchronous detector are the I and Q balanced demodulator stages. When the device is given an input signal, a reference signal is generated by the VCO. The DC output of the Q demodulator, which feeds into the VCO, causes the frequency and phase of the oscillator to zero in on the input carrier frequency and phase and then lock to it. The voltage-controlled oscillator then produces a plus 90-degree phase-shifted signal. This 90-degree phase-shifted signal is fed into the Q demodulator and into the minus 90-degree phase shift network. The output from the phase shift network then becomes the in-phase reference signal for the I demodulator stage. When the quadrature synchronous detector circuit is provided with both the input signal and the reference signal, it will produce an output which is derived from the difference of the two signals. If the L plus R and the L minus R signals are identical in frequency and 90 degrees out of phase, the output will be 0. If, on the other hand, there is a constant difference in phase other than the 90-degree phase shift, the output of the circuit will be a fixed DC value. Or if the phase is constantly changing, this circuit will produce an AC output. As you can see, the I demodulator provided the original L plus R audio information broadcasted from the stereo AM transmitter. However, it does not see the Q sidebands from the double sideband transmitter. The Q demodulator is also fed from the voltage-controlled oscillator section. But as you can see, its carrier reference signal is shifted plus 90 degrees. This allows the Q demodulator to see the Q sidebands from the stereo AM transmitter. It also causes this section to ignore the monaural L plus R signal. The system just described would be excellent for AM stereo, except that the envelope detector in the monaural AM receivers already in use can't see the I or Q sidebands. They can only see the vectored sum of the two. Therefore, the standard envelope detector is not capable of seeing the phase-shifted information. It can only see the RMS total of the amplitude modulation and carrier, regardless of phase. Here you see the block diagram of the basic sequom decoding circuitry. Notice that this system contains both a quadrature detector and envelope detector, like the one studied previously in the AM superheterodyne receiver. This system also contains a gain modulator, a comparator device, and a matrix system which is used to separate the left and right audio signals. You should now begin to see that the sequom signal is decoded by simply converting the stereo broadcast signal, which is already almost quadrature, to quadrature, then using a quadrature detector to extract the stereo L minus R information. In order to prepare the broadcasted signal for the quadrature demodulator, it has to be converted from the envelope detector compatible signal, which was broadcast, to the quadrature signal that was not envelope detector compatible. This is accomplished by demodulating the broadcasted signal two ways: with the envelope detector and with the I demodulator. The two signals are compared, and the resultant error signal is used to gain modulate the input of the I and Q demodulator sections. When the broadcasted signal is L plus R or monaural only, the transmitted signal is pure AM. In this situation, the envelope detector and I demodulator both see the exact same signal. This results in no error signal being generated from the comparator, in which case the gain modulator does nothing and the signal passes through without change. Now let's see what happens when a stereo signal is applied. You already know when the AM stereo signal is transmitted, it will contain both amplitude and phase modulation. This causes the signal being fed into the I demodulator to shift in phase, which results in the demodulated I signal losing some of its amplitude. The envelope detector, on the other hand, sees no difference in the amplitude modulated portion of the signal due to the phase modulation of the carrier. Therefore, the amplitude of the envelope detector remains the same. When the envelope detector and the I demodulator signals are compared, an error signal will be generated due to the difference in amplitude of the two signals. This error signal will automatically gain control of the input level to the demodulator stages. This action results in the input signal to the I and Q demodulator stages looking like a pure quadrature signal. This causes the Q demodulator to output the L minus R signal. The output from the Q demodulator is then combined with the envelope detector output in the matrix stage, where the left and right audio signals are separated. As you have seen, AM stereo is a combination of AM, FM, and television technology. When your studies advance you to television theory, you will notice the resemblance between the AM stereo signal and the color signal used in the standard color television receiver. This concludes the video on AM radio. We highly recommend that you view this video several times to gain the full benefit of the information which was presented to you. Review often and study hard if you wish to master the wonderful concepts of electronics.